So Steve, so I find the still participant, the number of participant is rising. So should we wait for a minute or so, or should we start now?
I think it's okay to wait maybe 1 minute. I wouldn't go too much more.
Okay, yeah, cool.
Should I go ahead and get my screen shared?
Oh yeah, why not? Go ahead. All right, so 1 minute passed. So yeah, I think it's a good time to start. So good morning, good afternoon, and good evening, everybody. So this is the second day, first session of SAZERAC 2 meeting, and this session is about the cosmic reionization and Lyman-Alpha emitters. So the format is of this talk is all talks are the 10 minutes in length, and 3 minutes for questions and 2 minutes to prepare for the next speaker. Okay, and you can write up your questions on the Slack. Okay, anytime you like. All right, and also the Anson will give you a 1 minute left notice to the speaker via chat. Okay. All right. So let's move on. So the first speaker is the Ryan Ensley, who is talking about a wide area view on reionization with MMT and ALMA, exploring massive redshift 7 galaxies and their host ionized bubbles. Go ahead, Ryan.
Okay, yeah, so for those of you who don't know me, yeah, my name is Ryan Ensley. I'm a student at the University of Arizona. I work primarily with Dan Stark, though the research that I'll talk to you about today has involved a number of other collaborators listed here at the bottom of the slide. So what I want to talk to you about today is a 3-year campaign we've been conducting with MMT Spec targeting Lyman-Alpha emission from UV bright massive Lyman bright galaxies identified across a very wide area of fields. Specifically, this survey has been focused on the XMM and Cosmos fields, which total about 7 square degrees of imaging. So what I'll describe in this talk today is how with this survey, we have been able to, 1, identify likely large ionized bubbles at redshift 7 via clustered Lyman-Alpha emitters in our sample, 2, quantify the galaxy overdensities in these likely reionized regions, and 3, uncover details of Lyman-Alpha transmission through the IgM at redshift 7 in these massive galaxies that's necessary to place our results in context of reionization. So first off, I just want to give some quick details about our survey. So far, we've observed over 90 massive redshift 7 Lyman bright galaxies. We have over 30 Lyman-Alpha detections at redshift 6.5 to 7.1, and a subset of our massive redshift 7 galaxies have also been observed with ALMA via the Rebel survey. So the first results from our Lyman-Alpha campaign have been described in 2 papers already published earlier this year. I'll quickly go through those results and then move on to what's new. So here on the left, I just want to quickly show the subset of Lyman-Alpha detections that we had from these initial results that were published earlier. So from these initial results, one of the things we found is that the Lyman-Alpha equivalent width distribution of our massive redshift 7 Lyman bright sample was similar to that we had from our redshift 6 Lyman bright sample that we targeted simultaneously. Okay, and what this means is that the Lyman-Alpha emission from massive redshift 7 galaxies is not being strongly attenuated by the highly neutral IgM. And this is in contrast to the Lyman-Alpha evolution seen in fainter systems, which does show a rapid decline consistent with what you would expect in this neutral IgM. Okay, so the question becomes, what's going on here? Why do we see this evolution in fainter systems and not so much in the massive galaxies. Well, one possible explanation is that this is giving us some insight into the structure of reionization. Perhaps what we're seeing here is the effect of massive galaxies commonly sitting in large ionized bubbles powered by strong overdensities. Okay, these bubbles allow Lyman-alpha photons to cosmologically redshift before encountering the neutral hydrogen, increasing their transmission through the IGM. Another effect that we might be seeing here at the same time is that massive Redshift 7 galaxies have large Lyman-alpha velocity offsets, which effectively give the same effect of boosting the Lyman-alpha transmission through the IGM by pushing the photons into the damping ring. So what we want to do moving forward is we want to better understand, kind of the contribution of both of these effects. So we're tackling this in two ways. One, we're building up a data set to identify and characterize likely large ionized regions at Redshift 7 across these wide area fields that we're targeting. And at the same time, we're obtaining deep Lyman-alpha spectra of our massive galaxies to explore how their Lyman-alpha line profiles impact the transmission through the IGM. So with the ionized bubble picture, we're tackling this primarily in the cosmos field just due to the deeper imaging available, allowing us to push fainter down the luminosity function. So our goal here is to identify the regions of clustered massive Redshift 7 galaxies showing Lyman-alpha emission across the cosmos field to determine whether these regions coincide with galaxy overdensities, and moreover, to characterize the extent of the Lyman-alpha emitters within these regions, giving us some insight into the extent of the possible ionized bubble that they sit inside. So from our first results, we noted that we had 3 extremely nearby massive Redshift 6.8 galaxies showing Lyman-alpha emission in the cosmos field. So all 3 of these galaxies are separated by less than 5 arc minutes, and they reside within a redshift interval of 0.06. All of these galaxies are contained within a radius of 1.7 physical megaparsec sphere. And just based on these massive galaxies, the number counts compared to what we have from the luminosity function suggest that these galaxies are tracing a overdensity of about 4 times the number of galaxies on 5 arc minute scales, 2 physical megaparsecs, if you want to think about it that way. So the question then becomes, are we seeing perhaps one of these instances where these 3 galaxies are kind of residing within this more extended, larger density that's powering this very large ionized bubble? Well, to kind of gain more insight into whether this picture holds, we need to better characterize the overdensity across a wider area. And we can do that, obviously thanks to the fact that these cosmos fields probe such a large area. So we've identified a total of 12 massive Lyman break galaxies with photometric redshifts consistent with redshift 6.8 in the surrounding 11 by 15 arc minutes squared, right? And we actually have another Lyman-alpha detection in the same region at a higher redshift 6.88, possibly suggesting that what we are seeing here is really this more extended overdensity, but we need to test this. So we conducted ultra deep, about 20-hour Lyman-alpha follow-up of the majority of these remaining candidates with the goal of quantifying the overdensity in this extended region and better determining the possible extent of the ionized bubble. So what did we find? We actually ended up with Lyman-alpha detections in 9 of 10 targeted galaxies across this region. All right, so that's a 90% Lyman-alpha confirmation rate in this region here, where all the Lyman-alpha detections have redshifts between 6.7 to 6.88. All targeted galaxies are massive, with UV luminosity spanning 1 to 4 times the characteristic UV luminosity, and all sources are contained within a sphere of radius 4.4 physical megaparsecs. Right? And now that we have this more extended region and 3D position information for these galaxies, we can determine that, based on these 9 massive galaxies, this region appears to be 2 times the average density across this very large scale, this 5 physical megaparsec, 15 arc minute scale. So this is one bubble that we've been able to identify so far. We're still pushing on it, but to better determine what these Lyman-alpha results are telling us about the structure of reionization, we also need to understand how the Lyman-Alpha line profiles are assisting in boosting the Lyman-Alpha transmission of these massive galaxies. So we're able to do that thanks to the decent resolution spectral resolution that we get from our binospec spectra. And we're also combining our results for a subset of sources that have C2 measurements from the ALMA Rebel survey. So I'll quickly go through those results in the remaining minutes. So what do we find from our binospec spectra? Well, we're finding broad Lyman-Alpha line profiles in our massive Redshift 7 galaxies, as you can see here. Substantial fraction of the photons are being pushed to high velocities purely as a result of their line profiles, which is boosting the Lyman-Alpha transmission through the IGM. So for reference, fainter galaxies show full with half max values of about 200 kilometers per second. We're also finding multi-peak line profiles in a subset of our massive Redshift 7 galaxies. And with our C2 measurements, we're able to place our line profiles into the systemic frame. So what do we find? Well, we find that all of the peaks that we're seeing are redward of systemic. Now, I don't have time to dive into the details, but if you're interested, please ask me after the talk. We're also able to measure the Lyman-Alpha velocity offsets of our sample, and we're finding velocity offsets that are systematically large, greater than 100 kilometers per second. And this suggests that these velocity offsets are indeed likely boosting Lyman-Alpha transmission through the IGM among these sources. With our sample, we've been able to double the number of velocity offset measurements among extremely luminous MeV less than -22 galaxies at redshift greater than 6. And combining our results with that literature sample, we find an average of 325 kilometers per second among these extremely luminous galaxies, consistent with model predictions. So in summary, we have this ongoing Redshift 7 Lyman-Alpha program targeting Redshift 7 galaxies across very wide area fields. We found that the Lyman-Alpha equivalent width distribution does not strongly evolve between Redshift 6 to 7 for the massive Lyman break galaxies. We're beginning to identify and characterize likely large ionized bubbles at Redshift 7 across the cosmos field. And we've indeed found one instance where we detect Lyman-Alpha in 9 of 10 massive targeted galaxies at redshift 6.7 to 6.88. That spans a large scale overdensity, 2 times the number of massive galaxies than I expected on average across a 5 physical megaparsec scale region. And this could potentially be powering a very large ionized bubble within this volume. We're at the same time with our survey, we're beginning to improve our understanding of Lyman-Alpha line profiles on IGM transmission. We find broad Lyman-Alpha line profiles among our massive galaxies, and we also find large Lyman-Alpha velocity offsets, meaning that a larger fraction of those Lyman-Alpha photons are being pushed into the damping wing, increasing their transmission through the IGM. Take any questions. Thank you.
All right, thanks, Ryan. So time for questions. Yeah.
Yeah, it looks like we already have a number of questions. So it says, what are the Lyman-Alpha luminosities? Also, do we know that they are really are massive galaxies, and what are their masses?
Yeah, so about the Lyman-Alpha luminosities, I haven't calculated those explicitly. That is something I can do. So sorry, I can't tell you offhand. I know that the equivalent lists range from about 5 angstroms to 40 angstroms in this sample. And they're all 25th, 26th magnitude, if that helps. The second question, sorry, what was the second part of the question?
Oh, do we know that they really are massive, and what are their masses?
So yeah, these galaxies, majority of them have IRAC photometry that is not strongly confused by neighboring sources, and I find masses ranging from about log m 8.5 to 10 to the 10. So, you know, on average about 10 to the 9 solar mass galaxies. Obviously, there are some galaxies in there that are closer to 8.5 that are just more bright because of the fact that they have more rapid star formation ongoing.
All right, thanks. So the next question from Rensky Smith. So the number of Lyman-Alpha detections in your redshift 6.8 bubble is impressive, and the Lyman-Alpha fraction seems even higher than that seen in sources at redshift 5. Do you understand why the intrinsic Lyman-Alpha fraction is so high?
Yeah, so it is worth noting that the O3 plus H-beta cumulative distribution in this region, I looked into this a little bit. It appears higher than that on average among the general Redshift 7 population. So maybe what's happening here is that these galaxies that we're sampling are preferentially have a larger production of Lyman-alpha photons just by chance, or maybe there's some environmental effect. It's something that I need to explore more. But I completely agree that's an interesting question.
Okay, so
Yeah. So another question is, have you tried fitting IgM models of the neutral fraction to the combined sample?
I have not yet. No, that's something that I hopefully will be able to tackle next year. But as I said, the survey is still ongoing. So, it's one of those things where we're waiting until we have enough data where we feel like we can really tackle them.
all right, so then the next question is Caitlin Casey, who is asking that what galaxy over density does the Redshift 6.8 structure corresponds to?
So the galaxy over density of this this region that I've described here. So it has 2 times the number of these UV bright massive galaxies than that expected on average across, this region that's about 5 physical megaparsecs in scale.
You have a number of other questions. If you can answer them in Slack at your convenience, we should probably move on in the interest of time.
Okay.
Okay, great. All right, so let's thank the speaker. All right. Okay, let's move on. So the next speaker is a Nakulu Gangoli, who is talking about the constraining reionization in progress at Redshift 5.7 with Lyman-Alpha Emitters.
Yeah, hi everyone. Thank you, Professor Ricci. Hi everyone. My name is Nakul Gangoli. I am a 3rd-year graduate student at UC Riverside. I work with Anson D'Aloisio. And so today I'll be talking about how to constrain reionization in progress at Redshift 5.7 with Lyman-alpha emitting galaxies. And to kind of give some broad context for what I'll be talking about today, there have been models that have been proposed which have reionization ending as late as Redshift 5. Which is actually very convenient for a lot of us since there are surveys already out there like SilverRush, which can observe LAEs at Redshift 5, 6, and 7, which means that they could very well be observing the tail end of the reionization process. And so what I want to do in this talk is to revisit large-scale structure statistics of LAE in the context of these late reionization models. And so to kind of further motivate what I'll be talking about large-scale structure, if we take a look at the SilverRush fields from the SilverRush 1 paper, we can see how there are some fields which display this large field-to-field variance as well as intrafield variances. For example, at Redshift 6.6, we can see how UD XSDS and UD Cosmos have this large variation in their densities. Whereas in DLA SIN 1 at Redshift 5.7, half the field is quite LAE rich and the other half is very LAE poor. And so the question that I kind of wanted to ask was, accounting for inhomogeneous selection effects, what are causing these large-scale density variations? Can they be explained due to just large-scale structure evolution alone, or does these large variances necessitate the need for neutral gas left from some late reionization model? And if it's the latter of the two, can we determine what the neutral gas fraction is? And if so, what tools are most adept at answering that question? And so what we first have to do is construct our mock LAE surveys. And the way we do this is we populate halos in a 1 cubic gigaparsec sized box from the MDPL survey, or from the MDPL simulation, such that we can get a large statistical sample of SilverRush sized fields, because the SilverRush sized fields are hundreds of megaparsecs off into a side. And so that's why we needed this huge box. And then the method that we use to populate those halos with LAEs is the method outlined in Weinberger et al. 2019. And I won't go into too much detail about what they do, but the important aspect of their modeling is that we implement a beta parameter, where this beta parameter in essence connects the circular velocity of a halo to the velocity offset from the Lyman-alpha line redward of the systematic. And as an example, here is a Lyman-alpha line. This is a Lyman-alpha profile where the line offset is centered at about 100 kilometers per second. Then to model our early and late models of reionization, we tuned the neutral fraction of the IgM using the excursion set model of reionization. And so what we do is we set, for our early case, we set the we set the neutral fraction to be 0% at redshifts 5.7 and 6.6. And then our late models include a 10% and 30% neutral fraction at redshift 5.7 and a 25% and 50% neutral at redshift 6.6. Then what we do is we tune beta specifically such that we make sure that we match our observational constraints, where those constraints include the Lyman-Alpha rest frame equivalent width, the LAE luminosity function, and the 2-point correlation function. We also make sure that we keep our mean LAE surface densities fixed between all our models. And that will kind of become an important caveat later on. And we set the mean LAE surface densities to be the same LAE surface densities in the Silverrush fields at their corresponding redshifts. And at the end of the day, we are left with 1,000 mock catalogs for each of our different models for a grand total of 6,000 fields of view. And so to kind of give an example of what we're dealing with, here are some LE catalog maps with redshift 5.7 on the left and redshift 6.6 on the right. And I show them with their given neutral fractions. And what we kind of begin to see is that where these points are the LAE and the shaded regions are the neutral gas, is that the more neutral gas that we seem to add, the larger these voids are getting in the LAE large scale structure distribution. And to kind of make that point concrete, if I blink between the two, we can see how not only are the the voids getting bigger, but the neutral gas is in essence relegated to those voids, but also that the LAEs seem to also be in essence sequestered to the high density regions in more neutral scenarios. And this is a direct consequence of us keeping our mean LAE surface densities fixed. What ends up happening is that the LAEs that are getting obscured in the neutral regions of the IgM have to be compensated for to make sure that LAE surface density stays the same. And so the ionized regions of the IgM become much, much more transmissive to the Lyman-Alpha line. And so then this comes back to the first question that I wanted to try to answer, was whether or not the large scale structure evolution could explain the wide field to field variations that we see in the fields, or that if that extra effect from neutral gas is needed to account for the variations. And so what we do is something that we call the split screen variance, where in essence, we take a given field of view and subdivide it along axes of symmetry such that we get roughly equal area and roughly similar shapes. And then what we do is we find the magnitude of differences between the different fields of view and normalize by the average surface density. And while this becomes quite simple in the case for our square fields, this is a little bit more difficult in the case of the Silverrush fields, which are a little bit more irregular in shape. But there are ways to kind of subdivide the field, like indeed deep in 2.3 that we do as an example here, where we kind of cleverly find different axes of symmetry and split the fields in different ways. And at the end of the day, what we find is that the Silverrush split screen variance is actually consistent with evolution from large scale structure alone and doesn't necessarily need neutral gas to explain the variations. But that being said, the more neutral gas that we seem to add, the wider these distributions seem to get, making it more likely in neutral cases to find these large intra-field variances, or these wide half-field differences in the LE densities. And so then that brings me to the second question. Well, okay, let's assume that there is neutral gas. Is there a way to find out how much of it there is, if it is there? And so the first statistic that we use is the void probability function, which has been looked at before. But in this context, we'll look at it in late reionization history, where in essence, the VPF is the probability of dropping a circle with radius r, and then the probability that circle contains 0 LAE. And so I show what that looks like for different scenarios, where this black line is the Poissonian distribution, where you randomly kind of throw points onto a grid and calculate the VPF for those points. And what we find is that when we start accounting for large scale structure statistic, or large scale structure formation, these voids get larger. But then when we add more neutral gas, as we saw before, these voids seemingly get larger and larger. And this makes this that qualitative fact more quantitative, where the voids are getting larger with the more neutral gas that we're adding. And that's because the LAEs are getting obscured in those low density regions. And I just as a caveat, these error bars that we see here we seem to be due to cosmic variance. We do the same analysis at redshift 6.6, but what we find is that there are actually larger voids at redshift 6.6 than at 5.7. But that's more so a thing because there's a lower LAE surface density of 6.6, and you can kind of see how the Poissonian distribution changes quite significantly because of that, and how all these curves change with respect to that Poissonian distribution. We also do deal with larger neutral fractions, but those are really only applicable to the blue and green lines. But at the end of the day, we see the very same idea where with more neutral gas, the voids seem to grow in size. And so while I talked about how adding neutral gas enhances the sizes of the voids, but now what about what's happening to these high dense regions? Can we quantitatively explain what's happening there? And so what we do here is use the peak probability function, which is the high density analog to the VPF. And it's a probability of randomly placing down a circle with radius r and enclosing a region with some density greater than a threshold density, which we set to be 2.5 times the mean LE density of redshift 5.7 and 2 times the mean LE surface density of redshift 6.6. And what we see is that, yes, there is an enhancement in the apparent clustering of the LAE, where these dense regions are getting more dense. Unfortunately, the error bars from cosmic variance are actually very large, and we attribute these to large correlations between the radial bins. And in essence, the dense regions tend to be closer to or within other highly dense regions, which makes it extremely difficult to use to constrain the neutral fraction. And we again do the same analysis of redshift 6.6, and we see the same thing. The apparent densities are getting higher and higher, but the error bars are quite large. And so now to kind of come back to the last question of how do these statistics stack up? Which ones are most adept at answering how much neutral gas there is? While the peak probability function doesn't do as well, what we do is we'll compare the void probability function to the 2-point correlation function, which is currently the most popular probe used today. It's kind of the gold standard right now. And what we do is we assume 2 different survey strategies: a silver rush-like survey where we sample 4 to 5 fields at a time, and a 10-field survey where we sample 10 fields. And then what we do is we bootstrap resample each case 10,000 times over and construct a chi-square distribution for a completely ionized IGF. And then what we do is we assume that we observe a curve which corresponds to a late reionization ending model, which is 30% neutral at redshift 5.7 and 50% neutral at redshift 6.6, and calculate the p-value of observing such a curve in a completely ionized IGM. And what we end up finding is that at redshift 6.6, the void probability function does about as well as the 2-point correlation function. But at lower redshift, at redshift 5.7, the VPF actually just does a better job than the 2-point correlation function. And this actually holds while we account for contamination effects as well. We test for contamination and find that it affects both of them roughly about equally. And so the intuition as to why the VPF might be doing better at lower redshift than at higher redshift is that at the tail end of the reionization process, the neutral gas is relegated to the voids. And since the large scale structures have more time to essentially evolve, those voids become more enhanced by the neutral gas present in the IGM rather than being more dispersed earlier on. And so I'll kind of conclude my talk there. I'll leave up a summary slide, and I will thank you for your time. I'll take questions.
Great, thanks, Nicole. All right, so then, yeah, please go ahead, Anselm.
Yeah, so there is already one question here. How do you model the escape fraction of Lyman-alpha photons on these large scales to generate the mock maps?
I'm sorry, could you say that again?
How do you model the escape fraction of Lyman-alpha photons on these large scales to generate the mock maps?
Oh, so what we do is we implement an IGM attenuation code. So if I go back here, similar to what happens in this curve. So what we do is we shoot skewers through the IGM and assume that assume that as we shoot skewers through it, the neutral fraction in essence. When we shoot a skewer through the IGM. Actually, can I get back to you later on that? I'm sorry. I need to.
Okay. Yeah. Sure. Yeah. Please, if you have any questions, please put them in the Slack.
Yeah. Sorry, I need to get back to you on that. I'm kind of getting flustered. I'm sorry.
Right. So I think there are now people are writing up the question, but okay. In the meantime, so let me ask a question. So short question. So I think that you assume the velocity shift of Lyman-alpha for 100 km per second.
Oh no! So we use the beta parameter to tune the velocity offset of the Lyman-Alpha line.
Okay.
When that's related to the circular velocity of the halo itself.
Okay. All right. So yeah, I thought it is fixed. So okay. All right.
No, it's not fixed. We change it.
Good. Right. So some more questions. Yeah. If not, I think the time is good. So all right. So yeah, let's thank Nakul again.
Thank you.
All right. So then let's move on. So the next speaker is the Rebecca Larson, who is talking about islands of reionization.
Thank you. Hi, I'm Rebecca Larson. I am finishing up my 5th year of my PhD at the University of Texas at Austin. And like Masami said, I'm going to be talking about a project called Islands of Reionization. I just want to give a shout out to all the people who have been part of this project. Thank you for all your work and your support and time. And if you have any questions going forward, please feel free to reach out to me. Because of the nature of this conference, I don't necessarily have to convince you why we study reionization. So we're going to just quickly talk about what part of reionization we're looking at. So we know that reionization ended around redshift 6. We don't exactly know when it started, maybe around redshift 15, but probably around redshift 10 or so, maybe 10% of the universe is ionized. And again, there's a lot of really great talks trying to narrow down some of these numbers. And so I just want to throw up the picture so that we, for completeness, have a picture of reionization. But I want to talk about how do we study galaxies themselves in the Epoch of Reionization, because it's a notoriously kind of one way to study the reionization process. Like, what are the sources that existed in the universe at that time? And so one of the ways we do this is looking for Lyman-Alpha. We can look for Lyman-Alpha in galaxies because it is attenuated by neutral IgM. So if you detect Lyman-Alpha, it's indication that you're in a ionized portion of the universe. And so if you look here, we show the fraction of Lyman-Alpha detected in Lyman-bright galaxies as a function of redshift. And we would expect for it to continue to increase, but around redshift 7, it really drops off. I know there's a lot of updated plots, but this one is very dear to my heart because it's very clear that we're seeing a drop in the Lyman-Alpha fraction at redshift 7, and this could be due to the fact that there is more neutral IgM at that time that's attenuating this Lyman-Alpha. And so a lot of this is studied the beginning or the end of reionization. And what we wanted to look at was further into the Epoch of Reionization. Let's try to study galaxies that existed in the middle of this process. And so depending on what you expect and how this process kind of happened, we either expect reionization to happen a little bit delayed and then rapidly the universe became ionized, or maybe it was a slower process and it happened more gradually. Whether you need a large galaxy to emit a lot of radiation, and so you need time to build up a large galaxy, you have this gray curve here from Brandt's work, and in where you have big galaxies starting later but ionize the universe faster to meet up with our observations at redshift 6, or you have smaller galaxies with higher escape fractions that start the reionization process a little bit sooner, and it doesn't have to be quite so dramatic, and so it's more of a gradual reionization of the universe, and that's this blue curve here from Steve Finkelstein's work. And so what we wanted to do was target galaxies that are in this time frame where these two models are the most discrepant. And so redshift 9, either you have expected 10% of the universe ionized or 60 to 70% of the universe ionized. And if you're looking for Lyman-Alpha in galaxies, you want to find those galaxies that are in those ionized pockets so that the Lyman-Alpha isn't as attenuated by the IgM and you can detect it. And so what we looked for is we targeted a set of galaxies that were in the Candles field that were photometrically selected to be at around redshift 9. We had great luck with the TAC at Keck, and so we had 8 nights over 4 semesters with this program, Islands of Reionization. We had J-band spectroscopy, and we had about 30 to so objects in our mass for each of our observations. And unfortunately, there aren't that many redshift 9 galaxies. So we have a target of 12 in our sample across these 4 Candles fields. And then we filled the mass with some other targets, which Taylor Hutchison is going to talk about in a few minutes. And so stay tuned for that. But this is our observations. We were looking for Lyman-Alpha at redshift 8.5. to 10.1. And so, this is the J-band observations that we took. We encountered some problems that were already known, as you observe for long periods of time on the telescope, maybe it's not super accurate, and the objects themselves drift in your slits, and so we had to account for this. I'm not going to spend too much time focusing on the data reduction since I've given that talk before, but if you have specific questions or encountering similar problems, please feel free to reach out. It's been a long process of data reduction. The other thing that we did is, after we accounted for this drift, we also incorporated the traditional Moss fire profile of an emission line, where we have a triple Gaussian, where there are 2 negative traces and there is a positive trace for real detection. But we were also finding that our objects were offset from where the pipeline, the traditional Mossfire pipeline, was expecting them to be. So here I'm showing where at this black line right here is where the pipeline expected our object to be centered, but we're actually finding it centered here. And so if you are using an extraction profile that is not quite lined up with where your source is, you aren't getting the full flux, and you need to make sure that you're lining it up. And this is easy to do when you can see your object, such as this emission line here, and so you can tell the pipeline where you need to extract the center of your profile. But for our galaxies, we were observing over multiple nights, but we couldn't detect it in one night, just by looking by eye in the 2D of where you needed to use your extraction profile. And so what we ended up doing is using kind of a rolling extraction. So we found that none of ours were offset more than 3 pixels. And so we have an offset of -1 to +3 pixels of our extraction profiles, which I'm showing here. Without knowing where our object was and needing multiple nights to get enough signal to stack together to see our galaxies, we needed to come up with a way of adding all of our observations together. And again, I'm not going to spend too much time on that because it was a whole long process, and I want to focus on our results. We have an automated line finding routine that was from my 2018 paper, where we look for emission lines in our data without any prior information using the MCMC chain. Again, I won't focus too much on that, so I'll just show our results. Here are all of the emission lines that we found in our data. And so I'm showing here the integrated signals noise of our emission lines on the x-axis and the sky RMS. So basically the error value on the y-axis here. And if you are to look at this plot, on the top left would be where skylines would be expected, and then the bottom right is kind of where you would expect real detections, where there's not a lot of error and you have high signals noise of your emission line. I'm showing all of our detections that we found. So like I said, our code is unbiased and it just does a search through all the wavelengths, but it's hard to kind of mask out the wings of skylines, and you're looking for very faint emission lines. And so trying to distinguish between these two things was a process of determining where we need to be making these cuts. We decided that sigma 5 seemed like a good indication of when we were expecting our emission line detections to be considered significant. And so you'll see that that's this vertical line here. Is anything above 5 sigma, we expect it to be more likely to be real. But we also did a negative test and contamination rates and things like that. So we find that our contamination rate is this horizontal line. So anything above that is not distinguishable from a contaminated or spurious detection or something like that. And so anything that falls in this bottom right part of the plot is what we would consider something that we want to take a look at, or a real detection. I'm also coloring them based on the stacked. So we stacked all of our nights together, and we have at least a 5 sigma detection in the stack of our data. But we also expect that if it's a real line, that you would see it in your multiple observations. And so all of those that are colored in red are lines that are found at greater than 3 sigma in both of our nights of detection. And so we consider something to be real and not noise or a hot pixel or a very bright cosmic ray that wasn't reduced if we detected it more than one time. And so I will show you just the one observation and the one detection that we have. Unfortunately, I'm not as lucky as Ryan with a very high detection rate, but 1 out of 12 ain't so bad, especially at redshift 8.7. So here is our Lyman-Alpha emission line. Here is the postage stamps from Hubble and from Spitzer, and our photo Z was around 8.9, but our spectroscopic redshift is at 8.7. I'm showing the 2 nights of observation here in the 2 colors, and then the black is the stack, with the red being our emission line fit and our signal to noise in all of those detections. You can see in the stack 2D the positive and the 2 negative traces. And so I just want to show a little bit about this galaxy itself. It is the second brightest one in our sample, and we would expect to be seeing Lyman-Alpha potentially from the biggest and brightest sources, the easiest with the current technology that we have before JWST comes out. And so we have an equivalent with the Lyman-Alpha about 4.7 angstroms. I'm showing some of the properties we measured of a galaxy using prospect or SED fitting, and here's some of the postage stamps again. And so what does this mean? We have a detection of Lyman-Alpha Redshift 8.7, and that's very exciting. But probably the more exciting part is that it's located physically really close to another object that's detected at that same redshift. And so if we actually look into our sample, we have what seems to be an overdensity by a factor of 5 of galaxies at redshift 8.7 in the EGS fields. And so we want to know how that has implications on reionization. And so we're going off of kind of the same thing that Ryan did, where we're measuring the ionized bubble size that could be created by these galaxies given their properties. And I'm showing what would happen if we had an escape fraction between 0 and 1. And even, if we have 100% escape fraction, we aren't always making a bubble big enough because we need at least a megaparsec for Lyman-Alpha to be transmitted. And so in order to see the Lyman-Alpha from these galaxies, you need to have a bubble big enough that's in that gray shaded area there. So we incorporated a luminosity function of all of the galaxies we'd expect that we wouldn't be detecting that would be in this megaparsec bubble size. And if we add up all of the flux from all of those, we still aren't getting enough ionizing radiation to produce a bubble, even 100% escape fraction, large enough that we would detect the detection that we have. But we need this overdensity factor. And so if we add in the 5 times overdense factor we have in this particular field, we would be able to see Lyman-Alpha from this galaxy because there's enough galaxies in the area that are producing ionizing radiation that's escaping, even at an escape fraction of something around 30%. And so if we change certain properties, we can do different things. Where we get a Psi value of 26, we could potentially also make a bubble this big if we had a higher escape fraction. And what's cool about this is these two properties are things that are going to be measured with JWST because this is in the EGS field, and this is where the Sears ERS program and some of our other data is going to be targeting. So we will be able to answer which one of these scenarios created this bubble such that we're seeing the Lyman-Alpha we're detecting. And so I will put up my summary slide here. I know I went through that really fast. So if there's any specific questions, please just let me know. And thank you.
All right, thank you, Rebecca. So time for questions.
So Danko asks, awesome work. Well, he's first. Awesome work on this great data. Looks like your Redshift 8.7 Lyman-Alpha detection showed strong oxygen 3 and Spitzer channel 2.
Yes.
Did your other candidates have similar Spitzer flux excesses?
Yes, this was actually part of our selection process for these galaxies. So in the photometry, we were selecting for those that had these red IRAC colors such that we would expect there to be high ionization parameters, also more likely to be in ionized bubbles this early on. So yes, that was intentional, and also kind of adds to the same picture of why we'd be detecting Lyman-Alpha in this galaxy.
All right. So, well, still the other people are writing up the questions. So, okay. Oh, okay. Rebecca Bowler is asking that, what is the error in your photometric redshift for the EGS source? Is the spec Z consistent?
Yeah, so here at the top right, we're showing the P of Zs for all 5 of these objects that are in our EGS field that are in our sample. And our spectroscopic redshifts, one for the Zitron object at 8.683 and then ours at 8.661, both fall within our expected, pretty much kind of around the 1 to 2 sigma significance of our P of Z. And so, yes, our photo Zs are consistent with these 2 spec Zs.
Right. So, any more questions via Slack? Right. Okay. Oh, yeah.
Yeah.
Christopher? Okay.
Yeah.
Go ahead.
Do you expect escape fractions of 30% at redshift 8?
I'm not quite sure that we could really put a measure on that, but we'll be able to to do a better job when we have more than just a Lyman-Alpha emission line. When we have J2T spectroscopy of this, and we can measure things like nebular emission, and that gives us kind of, some information about what's going on inside the galaxy. I would expect an escape fraction of 30% to be more likely than an escape fraction, in this range over here. But I will also caveat this was a pretty quick assumption and a pretty quick calculation where we weren't making escape fractions halo mass dependent, which we expect that to be the same, not the same escape fraction for all of the galaxies, which is what we did here in this calculation. And so when we have more information about the fainter galaxies that we're not detecting with Hubble, that we'll be able to see with JWST, and when we have spectroscopic observations, we'll be able to make that kind of measurement. But here it was just a simple kind of case study in how possibly we could be making bubbles this big. Escape fractions of 30% for smaller galaxies seem not unreasonable.
All right, so it looks like time is up and many questions on the Slack, but yeah, let's move on. Let's thank Rebecca again.
Thank you.
All right, so the next speaker is the Heather Wade, who is talking about why NBS probing the epoch of reionization with the brightest distant LAEs.
Yeah, so hi everyone, I'm Heather Wade and I am a second-year PhD student at Lancaster University in the UK, being supervised by Dr. David Sobral. Today I'll be talking to you about how we search for the brightest distant Lyman-Alpha emitters in the cosmos field, probing into the epoch of reionization using narrowband data taken with the VLT and the Hawkeye instrument in the hopes of populating the bright end of the Redshift 7.7 Lyman-Alpha luminosity function. As we all know, the epoch of reionization marks the last major phase transition of hydrogen and is a mysterious and fascinating realm in the very early universe. However, there are still plenty of open questions about reionization. How did the process of reionization develop? What are the start and end points of reionization? What are the sources of reionization? And what can we learn about these sources? So one model, patchy reionization, suggests that the brightest sources dominate the process. And evidence for patchy reionization can be seen when we observe galaxies and quasars through different lines of sight and see different levels of ionization. At the same redshifts, some fields can be fully ionized, whereas others can be fully neutral, suggesting a patchy process. So the exact relative contribution to cosmic reionization from massive stars and AGN are still unknown, as are the contributions from the many faint galaxies and from the rarer but brighter galaxies. And it's these bright galaxies that are thought to dominate the process. So in order to observe these brighter sources inside the epoch of reionization, we turn to the Lyman-Alpha Emission line. So many large surveys such as LAGA, Dawn, and SC4K have yielded great results by finding Lyman-Alpha emitters through various redshifts. For example, in Sobral et al. 2018, they observed 4,000 Lyman-Alpha emitters between redshift 2 and 6, and they find minimal evolution in the luminosity function, which is a key result for us to understand when we dig for Lyman-Alpha emitters above redshift 7 and observe how reionization affects the observability of galaxies here. But to even observe them in the first place, these bright galaxies need to be inside ionized bubbles that are large enough for the Lyman-Alpha emission line to be redshifted out of them, like this diagram shows. And this means that we can calculate the size of reionization bubbles. For example, the galaxy Kola 1, thought to be at redshift 6.59, has been calculated to require a bubble with radius 300 kiloparsecs to be observed. So this project, the results from this project will shed light on the size of ionization bubbles that were possible at redshift 7.7 by finding new galaxies here, following in the footsteps of Ush et al. 2015, for example, where they spectroscopically confirmed a galaxy at redshift 7.73. So in order to use the Lyman-Alpha emission line to find high redshift galaxies, narrowband surveys are carried out. And if your narrowband filter covers the redshifted Lyman-Alpha wavelength, you will see a transmission excess in the narrowband compared to a broadband filter at similar wavelengths, and you'll see your narrowband light up like this diagram shows. So a certain amount of progress has already been made in this field, with narrowband surveys discovering Lyman-Alpha emitters above redshift 6, which is shown here. But this plot is very busy, so let's break down this evolution a little bit first. So here we are seeing the Lyman-Alpha luminosity function at redshift 5.7 and 6.6, and this chapter fit is well established with plenty of confirmed Lyman-Alpha emitters above the bright and the faint ends. As I said earlier, we observe minimal evolution up to redshift 6. And above redshift 6, we expect that the amount of neutral hydrogen in the universe will mean that the fainter sources are no longer visible, which we see here with this drop in the luminosity function at redshift 6.6. The observed differences in the faint ends is possibly evidence of patchy reionization, as we would expect the real number densities of these two redshifts to be similar, but we miss the faint sources as they can only be observed if they are inside the ionized bubble of a brighter source. So as we move to redshift 6.6, we see a very different picture of the universe. These blue stars are showing the exciting new results from the Lager survey, Wald et al. 2021, which has observed the largest area of redshift 6.9 so far. This survey covered multiple fields, and they observed significant cosmic variance between them. For example, they found an excess of sources in the cosmos field compared to other fields observed, showing that a more ionized field shows a higher number of observed Lyman-Alpha sources. So this shows that the picture is far more complicated than us just being able to observe bright sources with faint sources disappearing in their clouds of neutral hydrogen. So more work must be done to interpret this, to overcome cosmic variance, and to push this to higher redshifts. So now, as we delve above redshift 7 and further into the epoch of reionization, the Lyman-Alpha luminosity function is even less established, with far fewer confirmed sources, and there is no consistency between studies or observed fields. So it seems like the faint end is once again getting pushed down, like we saw between redshift 5.7 and 6.6. But there's not enough data at the bright end to fully understand any evolution here. So there are two confirmed sources of redshift 7.7 from Tilvey et al. 2020 in orange. And our work aims to find more of these bright Lyman-Alpha emitters at redshift 7.7 to further populate the bright end of the Lyman-Alpha luminosity function, or at the very least, place some good constraints on it and use these to plan future wide, deep narrowband surveys. So these green lines represent the luminosities and volumes probed by the YMBS survey to find redshift 7.7 Lyman-Alpha emitters. The data for this work, the YMBS survey, was collected during a 44-hour observing run of the Cosmos field using Hawkeye on the VLT. The filter used was NB1060, making this a near-infrared narrowband survey. We observe a total of 69 pointings in the Cosmos field, with some deeper and some shallower, covering around 1 degree squared, with the survey designed to overlap with the deepest ultravista stripes. So we decided to reduce the data ourselves with a dedicated pipeline to get the best possible quality of data. And then to extend our search for redshift 7.7 Lyman-Alpha emitters, we include archive data for the Good South field, which was also collected with Hawkeye. So this single pointing is significantly deeper than the Cosmos data, with around 31 hours of exposure time in just this one pointing. So I don't have time to discuss the line emitter selection process, but we follow the methods of many other similar surveys, which includes cross-matching to catalogues of known photometric redshift values. So due to the nature of the surveys, our sample is dominated by lower redshift sources, but we can select these redshift 0.6 H-alpha emitters and calculate a preliminary luminosity function. So despite further work yet to be done here, our sample green is comparable to other, which is very good news. Studying these lower redshift galaxies is still very useful in order to better understand galaxy evolution. And this work will hopefully be coming to an archive near you in the next few months. So back to Lyman-Alpha emitters in the Epoch of Reionisation. Here in this ZJH color diagram, we exclude any sources with a redshift value below 3, and we highlight the approximate area where we'd expect to see Lyman break galaxies at around redshift 8. So once we apply the Z-band limiting magnitude, shown as these purple squares, we can see several sources here. After visual checks, we find that we potentially Lyman as a very preliminary result on the redshift 7.7 Lyman-Alpha Luminosity function here in black. So there's still plenty of work left to do here, but hopefully we can continue to better understand the trends in the redshift 7.7 Lyman-Alpha Luminosity function. So we can learn about the epoch of reionisation and the size of ionized bubbles that these sources produce. So look out for a paper with the final results of this soonish. Important future work in this field requires surveys across multiple fields to reach wide areas and overcome the field-to-field variance and to observe the bright end of the Lyman-Alpha luminosity function accurately. This intermediate luminosity region at redshift 7.7 is also yet to be fully studied and constrained, despite it being possible with current telescopes. A large sample through all luminosities is needed, and it is also especially important to follow up and confirm any sources that are found. The Lyman-Alpha luminosity function at redshift 8 is also unknown, and future technologies will hopefully probe this as well in the coming years. So I'll just leave you with the summary slide, say thank you for listening, and thank you for the opportunity to speak today.
All right, thank you, Heather. So time for questions. So now we are waiting for the 10-20 seconds for people to write up their questions.
Do the errors on your luminosity function point include cosmic variance, and do you expect cosmic variance to be important?
Yeah, we definitely expect it to be important. So this is the area we the full cosmos field. So already the volume is not super high. We'd need lots of different fields with high areas to overcome that. This is just a starting point, basically.
Right, so we got the question from Rebecca Bowler. Do the errors on your luminosity function point into, oh yeah, this is the same,
Yeah,
okay.
I asked that one.
Oh, it's the same, okay, all right, great. So anything else? Oh yeah, Yuichi Harikane asked a question. What are the UV magnitude of these sources? Are they UV bright?
So these two that we found here are very preliminary. So off the top of my head, I don't know. But that is definitely something that we would look into and try and confirm whether these are redshift 7.7 Lyman-Alpha emitters first. Yeah.
Okay, great. So I think the other time is the other running up. So yeah, all right. So yeah, let's thank Heather again. All right. So the next speaker is a Cristobal Moya, who is talking about the Lyman-Alpha double peak at redshift 7.
Can you see my screen?
Yes.
Great. So I will begin then. Okay, so good morning, good evening. My name is Cristobal. I'm a PhD student at the Pontificia Universidad Católica de Chile. I'm currently on my second year of my PhD. And today I want to talk about an interesting profile that we have found in one of our lager sources. So the first thing that I want to talk about is Lyman-Alpha profiles. So Lyman-Alpha profiles observed in the local universe in Greenpeace galaxies, such as the one that I'm showing you here. This is a figure from Young and collaborators 2016. You can see that you recurrently often find these double peaks in your Lyman-Alpha lines. The reason that you find this is due to radiative transfer processes. So as the photons try to escape from the region where they were emit, they either get absorbed, scattered, redshifted, blue shifted, and so on. So that's why you don't see a single peak, but you see this blue and red wing with a gap in the middle. I have included an arrow here for you to indicating this gap. And why is this gap important? Well, so the results from Greenpeace galaxies indicate that there is a correlation between the escape fraction of photons and the separation between the peaks. If you have a larger separation, you might think that you have more radiative transfer effects, thus photons have a harder time escaping the galaxy. If you have no separation at all, you might think that the photons are escaping without much travel, so you have a higher escape fraction. And also, I would like to remind you that these Greenpeace galaxies are believed to be analogs, low redshift analogs of the sources that are found in narrowband surveys such as LIGER. And you can imagine why the escape fraction is an important quantity for reionization studies. What about double peaks at higher redshift? Up to date, 3 Lyman-Alpha emitters have been reported at the redshift larger than 6. So you have Cola 1, Nebula 4, and A370. At this high redshift, as you go into the epoch of reionization, you would expect that the neutral IgM would absorb the blue wing of this profile. So if you see a double peak, you can think of two scenarios that are happening. Or sorry, you can imagine two things from your source. One is that there is an ongoing escape of radiation, because you can measure the separation between the peaks, and you can then imagine that the escape fraction is non-zero. And you can also imagine that your source sits within an ionized region of the universe. And due to the Hubble flow, the radiation, the Lyman-Alpha line gets redshifted out of the rest frame wavelength, and thus is no longer affected so heavily by the neutral IgM. Next, I want to talk just a bit about the LIGER survey. So LIGER survey is a narrowband survey that uses the special filter NB964. That is the one indicated in this plot by that orange arrow. The filter is installed in the DECAM instrument. So DECAM is really nice because it has a very good red sensitivity, as well as a large field of view of 3 square degrees. The filter is built such that the center matches Lyman-Alpha at a redshift of around 6.9. And we aim to obtain 30 hours per field, and are currently aiming to get 8 fields in total, meaning 24 square degrees. So once that we find our narrowband selected candidates, it's time to confirm them. Of course, you want to confirm these objects to see if you're actually able to find these Lyman-Alpha emitters at this redshift. So far, our spectroscoping campaign using the IMAX and LDSS3 spectrographs at Magellan Telescope have confirmed around 50 Lyman-Alpha emitters within the larger survey. So even though the spectra was taken to confirm the nature, we see that not all Lyman-Alpha emitters are equal. We see that there is some profile, there is some structure in their profile. But in order to study this properly, we need a higher spectral resolution. So the spectral resolution of this data is around 200 kilometers per second. So enter CDFS1. This is the object of interest. So in 2019, Yang and collaborators presented Magellan Fire spectroscopy for the brightest source in our Chandra Deep South field. Lyman-Alpha is detected at a redshift of 6.925. The goal of this study was to find nebular lines and to see the structure of the Lyman-Alpha profile. No nebular lines were found. There seemed to be 2 peaks in the Lyman-Alpha line, but the resolution they achieved was not so good as to make that claim of a double peak. We recently got new observations of this object with Magellan Fire. We got around 7 hours of exposure time with really good conditions, and we use a smaller slit than the one used in Yang et al. 2019. So the spectral resolution was around 50 kilometers per second. And our goal was still to find, to search for double peaks and see if we could secure any nebular lines. So let's go into the results. So of those 7 hours, we stacked 5 hours that were the one with the best conditions and the high signal to noise. The Lyman-Alpha line is clearly detected at both the 1D and 2D spectra. And also a double peak appears in both of them. You can see how the spectra has these 2 peaks, indicating a double peak, of course. But this wasn't enough. We wanted to see if we could say anything about the geometry within the slit of the system. So what we did next is that we stacked only the data that had the same position angle of the instrument. So this is important. I must mention that the fire spectrograph maintains a constant parallactic angle during your observations, meaning that the object will not have the same orientation in your slit throughout your observing run. So we stacked only the data that had a similar rotation angle. That left us with 2.5 hours of exposure time. Then we did 3 different extractions. We had this ABC. A is the lower one, right, the bottom one. Then we have B, the top one, and C, which include both extractions. So what we find here is that the double peak might not be due to radiative transfer effects and might be related to a velocity gradient. The reasoning behind this is that you can see that A has most of its flux redwards, whereas B has most of its flux bluewards, and the combination of both of them gives you this double peak. The separation of the double peak is around 100 kilometers per second, meaning a high escape fraction. Actually, from empirical relations taken at lower redshift, this would indicate a 100% escape fraction, but these relations had not been fully calibrated at high redshift. And the blue wing extends up to 120 kilometers per second from the line center. So as a conclusion and future work, we report the discovery of this Lyman-Alpha profile with a double peak at a redshift of 6.9. The small separation between the peaks suggests a high escape fraction, and the extension of the blue wing gives us a minimum ionized bubble, a minimum size for the ionized bubble of 0.14 megaparsec per megaparsecs. We are currently in the process of securing more sources with laggards with this we are in the process and we have obtained more spectroscopy data for us to further study this. In particular, see if there's any correlation with these profiles and the environment of the sources. Thank you very much. I will be more than happy to answer any questions.
Right. Thank you, Criswell. So time for questions.
So what are the Lyman-Alpha luminosities here? What is the Lyman-Alpha luminosity here? Comparable with low Z galaxies showing double peaks? And also another question is the continuum detected? Do you have an equivalent with?
Right. So I'll answer the second question then. So no continuum is detected on this source. And the Lyman-Alpha luminosities, this is bright. This is like a 43.3. Like the logarithm of the Lyman-Alpha luminosity is around 43.3. So this is the brightest source in our CDF field. But I do not know what are the typical luminosities of lower redshift galaxies that present double peaks. But I can tell you that this is on the bright end of our sample.
Right. So then next question is from the other Rohan Naidu. So how common is the profile you find among the green peas, low Z analogs? Does the imaging show any hints of merger?
Any hint of what, sorry?
Merger, galaxy
Right,
merger.
okay. So as far as I understand, these profiles are really common in your local green peas. Yeah, you often find this. I couldn't put a number to it. For as you go up to higher redshift, they become rarer and rarer because you need an ionized region for the photons to escape, and you need high resolution spectroscopy in order to resolve these double peaks. So they are not so common at higher redshift. As I mentioned, at this high redshift, there's only 3 of them found. But yeah, I mean, at low redshift, they are pretty common, but at higher redshift, not so much. But I'm unable to put a number to that.
How likely is it that something spurious appears given the noise, et cetera? If you just forward model the noise, how many times could an apparent double peak appear?
So in order to prove that, at some point what I did was just stack random exposures. So take a subset of the exposures. It consistently appeared. So the double peak was consistently found in both the 1D and 2D spectra. So we discard that, or yeah, we don't think it might be due to something spurious. Also in the Young 2019 paper, there were already some hints that this might be a special profile. And this has a rather high signal to noise. So we don't expect this to be a spurious detection. I'm sorry, I just realized that I didn't fully answer the previous question about the merger. Yeah, the narrowband image just looks like a single source. There's no hints for it to be a merger.
Right, thank you, dear Criswell. So I think many other questions are on the Slack, but yeah, it's time. So let's move on. So thanks, Criswell again. All right. So the next speaker is the last speaker of this session. So Taylor Hutchison, who is talking about near-infrared spectroscopy of galaxies during reionization.
Hi, thank you. Yeah, thank you to the organizers for letting me give a talk. I'm really excited to share what I've been working on this past year. So let's just dive in. We have heard a lot of really great talks already, kind of talking about why we care about the epoch, that's why we're all here, and then also motivating why the Lyman-Alpha Emission line in particular is really useful for probing into the epoch of reionization. So just to kind of springboard off of that, and then very quickly dive in. We're going to talk immediately about kind of some of the limitations that come from using Lyman-Alpha. So Lyman-Alpha is a resonant line. It's subject to scattering and is also heavily attenuated by neutral hydrogen. So often the redshift you would derive from Lyman-Alpha can be hundreds of kilometers per second redward from where the systemic or true redshift for a source actually is. And you can kind of see this in this example here, where I'm showing you this gorgeous asymmetric Lyman-Alpha profile, and the blue dashed line is the redshift we derive using Lyman-Alpha, which you can see is offset from where the systemic or true redshift for the source actually is. And you can quantify what that offset looks like with the equation on the bottom left, but mostly this would probably suggest to you, correctly so, that there is some kind of need for systemic tracer, something that's not attenuated by neutral hydrogen or outflows and can represent the true redshift of the source. Now, in the rest frame ultraviolet, there are a number of lines you could potentially use for this. This is an example, Lyman Galaxy composite spectrum from Alice Shapley's work, and you can see really strong Lyman-Alpha emission, and then we have these red lines highlighted, which are just a variety of nebular lines that can be used to trace the systemic redshift. Now, I do color carbon-4 slightly differently because it's actually a resonant line, and so it doesn't necessarily always trace systemic, but for the most part, you get the idea. And if you really want to pick a particular line for follow-up, if you have Lyman-Alpha already, you would probably have the best bet with carbon-3, just because it's often the second brightest line after Lyman-Alpha in the rest frame ultraviolet for these high redshift, low metallicity, high ionization galaxies, and also it's pretty ubiquitous for galaxies at these redshifts. But just in general, all of these UV metal lines are really powerful probes of what's going on within the stellar populations, give you insight into the ionization in these sources, and also tell you a little bit about the chemical enrichment in these galaxies. So all of it's really powerful. Now, here's just an example of some of the detections that exist at redshift greater than 6. There are more than what I'm showing here as far as detections, but there's not much more. It's actually really hard to get detections of lines other than Lyman-Alpha, just because they're so faint by comparison, and we're also in the near infrared at this point, so we're plagued by skylines if you're working from the ground. Something else I want to highlight here is all of these gorgeous detections I'm showing you, they all have Lyman-Alpha associated with them. And so for the most part, we use Lyman-Alpha to give us an indication of redshift, and then we follow up to get our actual systemic tracers. Something else I kind of want to highlight here is you kind of get this beautiful variety of lines. You can have carbon-3, nitrogen-4 and helium-2, or carbon-4 and O3. And so you can kind of learn a lot of different information depending upon the kind of lines that you have. So what have we learned from the UV detections that we have so far at these redshifts? Well, the star-forming galaxies that have been detected, for the most part, seem to have these subsolar metallicities, really hard ionizing radiation, and for the most part, young stellar populations that might include binary stars or an IMF that extends up to 300 solar masses. However, we could definitely use more UV detections from more galaxies, and ideally, lots of lines detected in a single galaxy to increase our constraints. So this is kind of where my work has started, my current work is coming in. So in order to increase the number of spectroscopic detections for galaxies in the Epoch of Reionisation, I've kind of started this program. It's pretty simple and straightforward. We are building a sample of galaxies from the literature that have Lyman-Alpha previously detected at redshifts 5 to 8. There's a priority sample, which I'll talk about in a second. And then we target the rest UV emission lines. And ideally, we would get detections of one or more of these. You can measure the systemic redshift from that, compare to Lyman-Alpha, get insight into the kinematics of the galaxy, and then compare it to all of your available photometry and all of your observations, compare to photonization modeling, and walk back any kind of inferred galaxy properties that you can. Just kind of piece together the narrative of this epoch and the galaxies that we're finding a little bit better. As a note, detections of more than one of these lines in a particular galaxy would significantly increase constraints on your stellar population properties. And actually, even non-detections can provide really valuable information. And if you're curious about what that means, you can check out my 2019 paper where we had an upper limit of silicon-3. So to kind of highlight what the program kind of looks like, using Keck, the Keck telescope and the MOSFER instrument, which is a gorgeous near-infrared spectrograph, you can kind of leverage this really beautiful sweet spot in redshift where you go from like redshift 6.8 to about 8, where you have some number of UV metal line emission in the J band, while simultaneously having some number of those lines in the H band. So the really cool part about this is, for a single galaxy, for example, with this spectrum at redshift 7, you can get 5 lines with these 2 bands if you were able to get all these detections. It is important to note that a lot of these lines might be really faint, but even upper limits can provide really useful constraints when comparisons to modeling. So for this work, we were awarded 8 J-band nights in 2018 to 2019 by work led by Rebecca Larson, which you've already heard about. This program was kind of a secondary science case for it, so we targeted redshift 5 to 6 sources. And then for this J and H band program, we were awarded 4 nights in 2020. We're still working through all the data and processing. Shout out to Rebecca Larson for an amazing job with the data reduction, and stay tuned for that awesome work. So to show you some of our preliminary results, I first want to show you this beautiful serendipitous O2 detection at a lower redshift. It's gorgeous doublet, the kind of detection we wish we could get at higher redshift, but okay. So what I really want to show you though here is you're seeing these really bright emission spikes in the center, this bright white light, and then you have these negative traces above and below. This is just a unique characteristic of data that come from instruments like Mossfire, where they employ a dithering technique to take data. So real things will look like this. So here are some of our tentative detections of UV lines at redshift greater than 5. This is preliminary, just as a note. And I could tell you what we think these lines are and what redshift they are, but honestly, I want you to stay tuned because I am actually more excited right now about a particular emission line, and I'm going to spend the rest of my talk talking about that line. So we have a carbon-4 detection at redshift 7.5, which I am way too excited about. It's really cool. You can see we've detected both parts of the doublet. So what you're seeing here is Mossfire 2D spectra on the top with this very faint detection. You can see the negative traces. And then we have our extracted 1D spectrum on the bottom. Now, another really interesting thing about this galaxy is it actually already had Lyman-Alpha detected. And so the velocity offset from Lyman-Alpha is about 120 kilometers per second, which is interesting because that implies that either Lyman-Alpha is being blue shifted relative to carbon-4, or carbon-4 is just more redshifted than Lyman-Alpha. So it'd be great if we had some kind of, spectroscopic tracer and a systemic tracer for this galaxy. And conveniently, we do. This galaxy has actually been very studied in the past, including my 2019 work where we got a carbon-3 detection for it. So this is just a stat sheet from that work. Feel free to go check out the archive paper for this. I'm not going to cover this in this talk. But using carbon-3 as our systemic tracer, we can then compare these lines relative to systemic. So the carbon-4 velocity offset from systemic is about 200 kilometers per second, which is pretty large, and especially large when you're considering the fact that the Lyman-Alpha velocity offset for this galaxy is actually only 88 kilometers per second. So this has been a really interesting conundrum that we've been encountering. A lot of interesting questions come out of this, right? What would be causing this offset in the first place? Why are they tracing different, why do they have different offsets? And why is carbon-4 way more offset than Lyman-Alpha? So there are some possible implications off the cuff we could think of. It could possibly be something to do with stellar carbon-4 contribution, maybe something to do with the optical depth in C3+, possibly something to do with the alpha velocity of high ionization gas. And there could definitely be more reasons. As it's a resonant line, there's lots of complications. So stay tuned. If y'all have any theories, I would welcome them. It's really exciting. But just looking at the line fluxes now and ignoring the offset for a second, if we compare it to our carbon-3 detections, you can see here what I'm showing you is carbon-4 over carbon-3 on the y-axis. And then we have IRAC color on the x-axis, where at this redshift, IRAC color is a proxy for the O3 and H-beta equivalent width. And you can see with all of these models that we're using, colored by metallicity, at the top right corner is where our points, like our observations, occupied, which indicates this really high ionization and really low metallicity, with these gray lines being 10% solar. This is really interesting, even for the stellar populations on the right-hand side that are single stellar populations with an IMF that only goes up to 100 solar masses. We seem to have this extreme region for these models that it occupies. So now that we have all of these lines detected, we can expand our modeling and go deeper and try and really pick apart what we're seeing here. But just to also compare to some previous measurements for some clarity for y'all. What I'm showing you here on the right-hand side now is the carbon-3 equivalent width on the y-axis and still IRAC color. And you can see that with those measurements, it's pretty good agreement with what we have with our carbon-4 measurement, less than 30% solar and an ionization log U greater than -2.5. So we're still seeing this story of this really high ionization, low metallicity system. Now it is important to mention that AGN might be a factor here. We could possibly have a weak AGN, and that's what we're looking at. There is a weak nitrogen-5 detection that was suggested from some GRISM data in 2016, although it wasn't seen in the 16-hour Mossfire spectrum. Or it could be a fractional contribution from an AGN, and a young, massive stellar population providing most of the ionizing light. That is still yet to be seen. We're going to be continuing this analysis, so stay tuned. I'm really excited to see what comes out with this galaxy. And yeah, that's it. So I will leave out my summary and I will take questions.
Right, thank you, Taylor. So time for questions.
It looks like we have a number here. Do we have constraints on helium-2 in this galaxy?
Oh, such a good question. Sadly, no. I mean, we know that helium-2 is pretty hard to model just in general. I would be uncomfortable placing an upper limit without actually trying to target this line. And this galaxy is perfectly placed in redshift where, using MOSFER at least, helium-2 does not fall in any of the bandpasses. So ideally, we'll target this galaxy using James Webb, all the wood. But no, I can't get any helium-2 right now. So I would expect it may be really strong, but I'm also just hesitant because it's so hard to model.
All right. So the next question is from the Joris Wistock. So do both lines of the carbon-4 doublet have a consistent velocity offset from systemic?
Yeah, that's a great question. They do. I can go back to that so y'all can look at it. Yes, they're both offset. They're perfectly separated based on the redshift you would derive. I did get this redshift from the first line just because it was stronger, but they are well offset. There is an interesting shape to the second line, which might have certain implications, which I don't feel like I should go into just because we don't have a good enough resolution for this, but they are offset the same amount.
As a kind of a related question is, how accurate is the velocity spacing of the carbon-4 doublet compared to theoretical expectations?
That's a good question. Honestly, I'm surprised that it is at this large offset. I would have expected the velocity offset for this based on at least what I've seen observationally. Theoretically, I would assume if you add in any kind of radiative transfer because the resonant lines, you could probably get some crazy stuff. But based on what I've seen observationally, I would expect it to be on par or within errors of Lyman-Alpha. Like at any other high redshift galaxies that have carbon-4 detected, in addition to Lyman-Alpha and another systemic line, they're within errors. So I'm surprised by this. I don't know if that actually answers your question. But.
Right. So the next one is probably the comment from David Sobral. So let me know if you want to directly compare. I was just checking that some AGN LAEs sources at redshift 2 to 3 have blue shifted Lyman-Alpha in relation to carbon-4.
That would be fantastic. Yeah, I'll get in touch with you because I want more examples to look at.
So maybe I think we have one more question, time for one more question.
Sure. Yeah. Do you have a plot of the Lyman-Alpha and carbon-4 line profiles together? It would be interesting to see the shapes as this could inform what is going on. It is not surprising to have Lyman-Alpha fill as close to line center as allowed by the escape physics.
That's a great question. I don't have a plot with them on top of each other, but I don't have a plot with them on top of each other, but that is a really good suggestion. I will make one that shows that. Lyman-Alpha is very much asymmetric in this galaxy, with a signal to noise of over 10 from the 16-hour MOSFER spectrum by Inte Zheng. But yeah, no, it's a fantastic question. I will look into that.
All right. So now all of the questions are running out. So oh yeah, maybe the last question. Okay, from the John Chisholm. What is the carbon-4 equivalent width? Also, what is the carbon-4 doublet flux ratio?
That's a great question. For the equivalent width, I've not yet calculated that. I'll be using broadband photometry to approximate that like I did with carbon-3. So stay tuned for that. But as far as the flux ratio is concerned, it's pretty close to 1, but the first line is larger. I've seen examples where the carbon-4 flux ratio is about 1.3 with other sources that kind of match at lower redshift. It seems to be about that for this source as well. Yeah, so stay tuned. We'll look more into that.
All right. So now all right. So I think it's time. So yeah. All right. So thank you, Taylor, for a nice talk, and let's thank all of the speakers in this session. All right. So this is the end of the first session of the second day. And now we are moving on to the coffee discussion break. So see you in 45 minutes.
And just a reminder, if anybody wants to do some socializing, the Wonder Me room should still be open. So please go ahead there if you want to chat with people. It worked quite well when we tried it yesterday.